Hello everyone, welcome to Physics Vault, and today we will study modern physics. Today is the lecture 1 of modern physics, and today we will study photoelectric effect. So let's start. Our first topic is proving the dual nature of light with photoelectric effect. So we know that light is a wave and it has particles as well. It is not a single nature, it has a double nature. It is a wave and a particle at the same time. Wave, as you can see here, but packets are photons. These particles are actually photons. So, photons are particles and wave is a wave. So, we know that light is a wave. But how do we prove that light is a particle made up of particles known as photons as well? So, to prove that, we have an experiment which is known as the photoelectric effect. How do we do that, you may ask? To do the photoelectric effect, we put light on a metallic surface and electrons are ejected out from it. So let's go to the microscopic level and see what is happening inside. As we can see, this is a metallic atom. This is the atom of a metal. So one question may arise that why do we choose metals and not any other material instead? So to answer that, we can say that metals are highly conductive, so they will show more photoelectric effect, and other materials are not as conductive, so they won't show as much photoelectric effect. So to measure most photoelectric effect, we use metals. Okay, let's see what's happening here. We use photon. We put a light ray on the metal, so the photon is going on an electron. It is a particle, and electron is also another solid particle. So, for example, this is a electron and this is a photon. Comes here and electron goes out. So it transfers its energy into the electron. So electron goes out. That's what's happening here. Electron is going out of the atom. It is ejected out. How it is ejected out? Because the photon has transferred its energy into the electron. So now let's do the mathematics here. How do we calculate how much energy and what is happening? So as we can see, EP, which is the energy of the photon, is denoted by EP, and there is this written here, which is phi. Phi is the work function. Work function is the minimum energy which is required to pull the electron out of the shell, out of here, out of the atom. How do you pull? You have to give it some minimum energy to pull it out. If you give less energy than that, it won't come off the atom. Electron will stay as is. But if you give more energy than the work function, electron will eject out of the atom. So we need it to be ejected out. So we give more energy. So the energy of photon should, when it is more than the work function, we can see that photoelectric effect is taking place. Now we can see here that the energy of proton is defined as hf, h being the Planck's constant and f being the frequency of the wave, which can be also written as hc by lambda, lambda being the wavelength and c being the speed of light, and h is the Planck's constant again. Now energy of photon is the energy and work function is also energy. So work function, we can define it as hf naught. F naught is the threshold frequency. So threshold frequency is a frequency which is the least frequency which is the exact frequency that can make hf naught equal to the energy of the work function. So work function is some energy, it is a predefined energy. So when you multiply h by f naught, you will get the work function. So that frequency is f naught. Now we do some maths here. As we know that EP should be more than phi, so hf should be more than hf naught. H gets cancelled, so f should be more than f naught. So the frequency should be more than threshold frequency for photoelectric effect to take place. Okay, so now let's actually calculate the energy of the photon and the momentum of the photon. So energy of the photon, we can see that it is defined as h times f, which is defined as h times c divided by lambda. So we can write it with the values. So H value is 6.64 into 10 to the power minus 34. C value is 3 into 10 to the power 8. And R, we can see that we have used electron volt. So what is electron volt? That is a unit of energy. How do we convert it? It's joules. 1 electron volt is equals to 1.6 into 10 to the power 19 joules. So we add it there. So to get the final answer in the electron volts. So now these all are constants and we have one variable which is lambda. Now all constants, when you calculate, it comes out to be 1242. And when you divide it with our lambda, and the answer comes as the energy of the photon in electron volts. This is a beautiful result you can memorize. So to solve the questions, directly put the value of lambda here and you will get the value of the energy of the photon. Okay, so we are done with the energy of the photon. So in the next lecture, we will cover intensity of light, what is intensity and how to calculate it. And then we will do some numericals on the photoelectric effect. And we will see that how Einstein found the photoelectric effect in the circuits. And we will draw some graphs as well. Thank you.